I'm now in Octave, and we are looking now at the file norcow.m. You can find this file in the repository next to this unit. I will start with x equal 2 because I would like to evaluate this base rule for value x equals 2. And I would like to make 100,000 simulations. Since I would be simulating base rule that would be ratio of two integrals, the numerator would be one integral, denominator other integral, and then I'm going to take the ratio. Let's take first a look how to solve this using simulation from the normal distribution with mean x and variance 1. This was the first approach in the simulation that we did. So for these n simulations, n is 100,000, I'm simulating theta to be normal with mean 1 and 0 and shift that mean 0 to x. So this theta equals x plus random normal is simulating a number with normal distribution with mean x and variance 1. And then the numerical, in the numerator, I have the theta 1 plus theta squared. And denominator, I have 1 over 1 plus theta squared. What I'm doing here, I'm making the sum. At the beginning, the numerator and denominators are equal to 0. And in this loop from 1 to n, I'm adding these simulated functions that we call g involving thetas. When this loop is finished, my base rule at 2 would be simply ratio numerator over denominator. This is done using the simulation of the normal part of the integral. As I said, you can do this simulating from Cauchy. So I'm starting with x equals 2, again, 100,000 loop. Numerator is 0 at the beginning, denominator is 0 at the beginning. And then in this loop, I am simulating bivariate normal with mean 0 and variance 1. And Cauchy can be obtained quite simply as a ratio of two independent standard normals with mean 0 and variance 1. So simulating the random normal bivariate and taking the ratio of the components gives you a Cauchy. Now, this theta, which is Cauchy, should be plugged into the function that is exponential, remember. Theta is theta times the function which is having this exponential part in the numerator and simply exponential part in the denominator. I'm summing those to the numerator and denominator, which are zeros at the beginning, and at the end of loop, I simply take the ratio. Now, 1 over n that we had in these approximations canceled in the numerator and denominator, and simply I'm dividing these two sums. So let's run this. If I run this, both of them, in the command window, the result is that delta at 2 in first way, simulating from normal, is obtained approximately to be 1.2700. And if I simulate Cauchy's, the rule is delta at 2 is 1.2844. Let's now take a look how these integrals, ratio of the two integrals that we just did by simulation, can be done numerically. For that purpose, I have the Python file in which I have the expressions in the numerator, an expression in the denominator, and simply I am taking the numerical integral. For that, I need scientific Python, CPy, and to import from that, integrate infinity and exponential function, and making these two lambda functions. One is for numerator and one is for denominator. And then rule delta 2 is simply to integrate the numerator between minus infinity and plus infinity, and divide by integrating denominator between minus infinity and infinity. This numerical integral returns two values. One is the approximation, the value, and second is the error, estimator of the error made. So the 0 and 1 values in that result sequence, 0 corresponds to the value and 1 corresponds to the error. So to get the ratio of the two integrals, I'm taking the ratio of two 0 values of the result, and delta 2 is 1.282195 and so on and so forth. Now, what error is made? I'm taking the error in the numerator, and that error in the numerator is of the order of the 10 to the minus 9th, and the error in the denominator, which is of the order of the 10 to the minus 8, and I'm calculating the error of the ratio of the two integrals. It is simply error of the numerator dividing by the value of the numerator, error of the denominator dividing by the value of the denominator, times delta 2, times the ratio. And the error that we made by this numerical integration for this ratio is of the order 2.3 times 10 to the minus 8. So it is quite precise. Python gave you a little bit more values than needed. So probably these far decimal places are not correct, but the first 7-8 decimal places are correct, and the value of the integral of the ratio of the integrals is 2.8282195 and so on and so forth. Notice that this value is close to what we got by simulation. Not exactly, the simulation is approximate, but it is good approximation.